Right, my job is to try and explain to you what the Kudla program is. And I mean, I don't know either. I can tell you what it means to me personally, which is just anything that grew out of a series of papers that Kudla and Millson wrote in the late 1980s, so 40 years ago now. And the short version of what Kudla-Millson theory is a geometric version of theta series. So for orientation and to fix notation, I'm going to start by reminding you about some classical theta series. So throughout the talk, we're going to fix a rational quadratic space. And there's a bilinear form associated to it, which I will always normalize in the number theoretic fashion. So it's going to be square brackets xy is q of x plus y minus q of x minus q of y. And we're going to fix a lattice. L and V, on which the quadratic form is z-valued. Okay, so the origin, the very first result is due to Jacobi. This is something like 1820s, 1830s. You probably all know this, I assume. I mean, it's in Sayre's course on arithmetic, which means everybody should know it. Assume that V is positive definite. Then Jacobi proved, so tau is going to be an element in the upper half plane. Q is the usual e to the 2 pi I tau. The theta series associated to the lattice, you just form the formal Q expansion whose coefficients count how many times your lattice represents a given integer. So Q of tau is going to be the sum over m greater than or equal to 0 of the number of lattice vectors of norm m times q to the m. And the theorem, that's not a statement, assume this, is a modular form of weight half the dimension of the quadratic space. So in Sayre's book, he proves this in the special case where the lattice is self-dual, in which case you get a modular form of level SL2Z. Of course, Jacobi used this to strengthen Lagrange's theorem on sums of 4 squares by actually giving a formula for the number of ways that you can write a positive integer, a sum of 4 squares or a sum of 8 squares, by computing the appropriate theta series and showing that they're actually equal to Eisenstein series, whose coefficients are easy to describe. So then about 100 years pass, and Siegel comes along. So now, let's take a positive integer d, define the Siegel half space. Of degree d or genus d, depending on who you ask. HD is the set of all tau equals u plus iv. So these are going to be now tau is going to be a d by d matrix such that the real and imaginary parts are symmetric, so tau is symmetric. And V is positive definite. So this is my notation for symmetric d by d matrices. The symplectic, the 2d by 2d symplectic group acts on this in the usual way. So if I write my symplectic matrices as block d by d matrices, then A, B, C, D acting on tau is, I never remember the order, A tau plus B times C tau plus D inverse. And if I give you symmetric d by d matrix with rational entries, it determines a holomorphic function on the Siegel half space called q to the t by q to the t equals e to the 2 pi I. You take t and tau, multiply them as matrices, and take the trace. And so here's Siegel's generalization of Jacobi's theorem. Siegel says, why stop at just counting how many times the lattice represents an integer? Let's count how many times the lattice represents a fixed matrix. So theorem of Siegel. So these are the original Siegel modular forms, still assuming that, that our lattice is positive definite. Can define theta L of tau to now be, I'm going to sum over all symmetric d by d matrices. I'm going to count the number of d tuples of lattice vectors such that q of x is equal to t times q to the t. Let's do this. So this is a Siegel modular form. Of the same weight as in Jacobi's theorem. And what does this q of x mean if x is a d tuple? Well, q of x is the moment matrix of the tuple. So here, if x is a tuple of vectors, q of x is the symmetric d by d matrix that you get by taking the matrix of inner products, but you put a 1/2 in because we're using the number theorist normalization. So it's the matrix xi xj over 2 in sim dq. And basically, Siegel defined a Siegel modular form in order to make these Siegel modular forms. They are the original Siegel modular forms. Okay. So that's the prehistory. So now let's try and make things more geometric. So Kudla and Millson work in a much, much greater generality than I'm going to explain. I'm going to stick to the simplest and to me most interesting case. So let's talk about orthogonal Shimura varieties. So Kudla and Millson, they say, well, let's drop the assumption that V is positive definite and allow arbitrary signature. And you can then look at the orthogonal, the special orthogonal group for your quadratic space of arbitrary signature. And there's always you can attach a locally symmetric space to it, which is going to be some Riemannian manifold, but it's not usually going to be a complex manifold. So I'm going to restrict to the one signature that actually gives you a Shimura variety, a complex manifold. So suppose V has signature n, comma, 2. The 2 is important. Okay. And G is going to be the special orthogonal group. So I'm thinking of it as a reductive group over Q. And the real points, G of R, acts transitively on the following complex manifold. D, so this is going to be, so we take our quadratic space, we complexify it, extend the bilinear form to a C bilinear form on the complexification, look at all the vectors that are isotropic and have the property that the pairing of Z with its complex conjugate is negative. In particular, Z can't be 0, mod out by the scaling action, and so you think of this as living inside of the projective space of our complexification. So inside of projective space, we look at the hypersurface of isotropic vectors, and then we impose this open condition. So we started out with something of dimension n plus 2, we cut it down to n plus 1, and then we took a hypersurface. So this is dimension n. Okay? And then let me just say, I mean, this is a little bit sloppy. So in fact, this pair, G comma D, is a Shimura datum. There's a natural way to realize this D as a conjugacy class of these maps from Deligne's torus into the real points. But I'm not going to write down what that is. With reflex field Q. The Shimura varieties associated with this Shimura datum are not of PEL type. They are not generally moduli spaces of abelian varieties. They are always of abelian type, which in this particular case means there's another Shimura datum associated to the G-spin cover of SO, and then this G-spin Shimura datum embeds into a Siegel moduli space. So what that means is that if you fix a level structure and look at the associated Shimura variety, you can always pass to some Étale cover of it, which embeds into a moduli space of abelian varieties. So up to that Étale cover, there's something like a universal abelian variety that lives over these Shimura varieties, but they're not literally moduli spaces, except in some extremely low dimensional cases. Like in signature 1, 2, you get modular curves and quaternionic Shimura curves. In signature 2, 2, you get Hilbert modular surfaces and quaternionic variants of Hilbert modular surfaces. In signature 3, 2, you get the Siegel moduli space and quaternionic variance of the Siegel threefold. In signature 4-2, there's a moduli interpretation that's kind of complicated. In signature 5-2, there's nothing. In signature 6-2, there's a really complicated moduli interpretation. There's nothing after that, except that when you go all the way up to signature 19-2, I think, it's a moduli space of polarized K3 surfaces, which means if you go down from there, there are moduli spaces of K3 surfaces with more and more polarizations. But then after 19-2, there's just nothing that anybody knows.
Are you allowing n for 0?
No, because this would be false. Picky. N is at least 1. Thank you. Okay. This Shimura datum and the associated Shimura varieties have some extra structure on them. So what is the extra structure? One, there's an obvious holomorphic line bundle on this. You just restrict the tautological bundle from projective space. Let L be the restriction to D of the tautological bundle. I.e., if I take a point, Z, in my Hermitian symmetric domain, the fiber at Z of this tautological bundle is the line spanned by Z inside of V. It's not just a holomorphic line bundle. It even comes with a metric on it, which if timing goes well, will be important later. And if timing doesn't go well, will never appear again. 2, L has a metric that I'll call norm square. If I have, a perfectly good, it's a line. So if I want to tell you what the metric is, I just have to tell you what the absolute value squared is of a single vector in the line spanned by Z. So I'll tell you what the norm of Z is. The norm of Z squared is, okay, the definition of D is still there. There's an obvious positive number floating around. I take the inner product of Z with Z bar divided by 2, and then put a minus sign in front. So it's a metrized line bundle. And 3, maybe the most important thing. There are lots of sub-Shimura varieties on it that come from embedding smaller orthogonal groups. So you can sort of parameterize these in a nice way. So there are special cycles. In any codimension, D. So here's how you define them. So if I give you any vector in the real points of my quadratic space, I can define D of X to be those isotropic vectors in D that are orthogonal to my given vector. And what does that look like? Well, this D of X is it's a smooth codimension 1 complex submanifold, so a divisor. If my vector has positive norm. If X is 0, I visibly get all of D. And it's empty in all other cases. You can check. It's a consequence of the signature condition. That's an easy linear algebra exercise. And then more generally, if I give you a D tuple, of vectors, we're just going to define D of x to be the intersection of, well, the usually divisors associated to the components. I mean, you can intersect them in the naive set theoretic sense or in the sense of a complex analytic space, and you'll get the same thing. It's always a smooth submanifold whose codimension, so a smooth submanifold, complex submanifold of codimension the rank of the moment matrix of my tuple, rank Q of x, which is somewhere between 0 and D.
So when you find symmetry, there is another symmetry, but it is only up to theta.
Sorry? Oh, yeah, okay. I mean, I'm deliberately abusing notation. Sometimes Z means the vector, sometimes Z means its span. It's usually it will, if it's not clear from context, it means it doesn't matter. I mean, here this condition is unchanged by scaling Z. So I'm going to go back and forth between a Z and a line and Z being a vector. Does that answer your question? Ah, right. I mean, here, this, I mean, Z is a line. Pick any vector on that line, call it Z2, or call it Z as well, and the norm of that vector is this. So here, right, here Z is literally a vector, not a line. But it specifies the absolute value on all vectors in the line. Okay? Right. And let me remark, this is empty unless T is positive, unless the moment matrix, Q of x, is positive definite, a positive semi-definite. Again, it's a consequence of the signature condition. Okay, so I mean, on the Hermitian symmetric domain for our Shimura datum, we have this huge collection of interesting cycles in all codimensions. So now we want to assemble them into cycles on the Shimura variety that you get by passing to some quotient. Okay. So let's fix a lattice. On which the quadratic form is z-valued. And some arithmetic subgroup gamma inside of the special orthogonal group stabilizing the lattice. You could fix the lattice, take gamma to be its full stabilizer. You could fix your arithmetic subgroup and then choose your lattice to be stabilized by it, but whichever you prefer. And then, okay, so I'm going to do something that's supposed to remind you of Siegel theta series. So now, if I give you a symmetric D by D matrix, I can go up to the Hermitian symmetric domain, look at all the d tuples of vectors having that moment matrix and just formally add up all of the associated cycles. And then because my lattice is stabilized by gamma, that'll descend to d mod gamma. So I just have to write that. Define an analytic cycle z of t, the sum over all d tuples of vectors in my lattice of the specified moment matrix of the associated cycle of codimension, the rank of the moment matrix. Of codimension rank of t on d mod gamma. Okay. Okay, so of course d mod gamma is a quasi-projective algebraic variety. This turns out to be an algebraic cycle on this quasi-projective algebraic variety, essentially because you can realize this as a formal sum of images of smaller Shimura varieties. So it's not just algebraic, but when you pass to the canonical model of this, copies of this, this will actually be defined over the reflex field Q. But in particular, because d mod gamma is an algebraic variety, we can talk about its Chow group. And the fact that we started with a d by d matrix and ended up with a cycle of codimension rank t is somehow a defect. We really wanted to get a cycle of codimension d, which you don't quite literally get a cycle, but we've got this tautological bundle floating around. So codimension rank d and a cycle class. So I want to distinguish between the physical cycle and the cycle class. My cycle class C of t in the Chow group of cycles modulo rational equivalence. I'm gonna take the naive cycle that I already have, and to get in codimension d, you take this tautological bundle, you take its dual, which is in the Picard group of gamma mod d, but the Picard group is the same as the codimension 1 Chow group. So in the Chow ring, I just take the naive thing and I intersect it with enough copies of the inverse of the tautological bundle to end up in codimension d. So L check, d minus the rank of t times. And so in this lecture, I'm mostly going to just work with d mod gamma. But let me just say, or maybe let me write on the board something that I already said out loud. So remark. If we fix some compact open K inside of the adelic points of our special orthogonal group, so stabilizing some lattice L, then we can form the usual Shimura variety. Is a disjoint union of these quotients in the usual way. for now at some varying choices of gamma. If M is then the canonical model over Q, and you just repeat this construction on every one of these D mod gammas, and you get a cycle class that's actually defined over the reflex field. Okay, so I said there was this series of, I think, 3 papers of Kudla and Millson between 1986 and 1990. And the upshot of these 3 papers is the following theorem. So we've got these classes in the Chow group. There's a cycle class map from the Chow group into cohomology of the complex points. So let's take these cycles, apply them. So after applying, the cycle class map. The formal generating series what am I calling this? Theta Km. So here, tau is in the genus D Siegel half space. Theta Km of tau, you take the sum over all symmetric D by D matrices of this cycle class, but in cohomology. So this is a formal generating series valued in cohomology. Cohomology double bracket Q is a Siegel modular form. Of the expected weight, half the dimension. And whenever I say that some generating series valued in some vector space is a modular form, where am I? Yeah, I'm here. I'm going to leave that. So, where modular becomes modular after applying any linear functional in cohomology. Coefficient by coefficient. Take any linear functional at all, apply it coefficient by coefficient to that generating series. The result will be a Siegel modular form. Okay. So that is the upshot of their 3 papers. Right, so that I think that appears in the last paper from 1990. So then you jump ahead 20 years.
Sorry.
Yeah.
What do you need to pass to canonical model?
Canonical model. I mean, I really want this in de Rham cohomology, singular cohomology. So I'm really talking about the complex fiber. This is it's a statement of the complex manifold. But the cycles are initially defined on the canonical model, yeah.
So there are also results of this sort of general signature RS.
Yeah, right. So, right, I mean, like I sort of mumbled incoherently. Kudla-Millson really work with a quadratic space of any signature, RS, for example. And you can still form something like that, but it's not going to have a complex structure. It's just going to be a Riemannian manifold. But the statements, you can still form the cycles, and you just replace this with this locally symmetric space, the Riemannian manifold, and there's an analogous modularity theorem. And they all, I mean, in the next lecture, we're going to switch from orthogonal Shimura varieties to unitary Shimura varieties. They do it in much greater generality than what I'm saying here. I just want to stick with what to me is both the easiest and most interesting case. Because what I hope to do, yeah, maybe, is actually sketch the proof of this. And for these orthogonal Shimura varieties, it's actually much easier. Like you can write down an explicit, but hopefully I'll get there. The proof in full generality is very difficult. The proof in this special case you can kind of do by hand. Okay, right, so 20 years later, there's a stronger result of Brunier and Raum, building on work of Li-Zhang and Borchards, which says that you never needed to pass to cohomology. The same statement was already true on the level of the Chow group of the canonical model. Modularity already holds for the same theta km of tau equals the exact same formula, but now in the codimension D Chow group of the canonical model. And that only makes sense for this signature. Not Raum. Okay. Just to say a few words about this. So why are there so many names? Borchards proved the case where D is 1, the generating series of divisors. And he did this by writing down Borchards products, which are rational functions on M, or more generally, rational sections of this tautological line bundle. Lots of rational sections whose divisors are supported on the special cycles of codimension 1. So every time he writes down a rational function whose divisor is some linear combination of the special divisors, that's saying that that linear combination of special divisors is 0 in the Chow group. So every one of these Borchards products that he writes down gives you a relation in the Chow group. And amazingly, he proves that the relations in the Chow group that he's able to produce are precisely the ones that imply modularity. Li-Zhang's unpublished thesis, he used Borchards' result in codimension 1 to prove the theorem in any codimension, except he couldn't prove that the formal generating series actually converges. So he proved that if it converges to a modular form, a Siegel modular form. And then Brunier and Raum proved the convergence, completing the proof. So there's 3 big steps, all of which are very difficult to explain. And so I'm not going to say more than what I've just told you. I'm going to spend the rest of the talk focusing on the Kudla-Millson proof. And there's more, if there were more time, there are more theorems. Like I said, these Shimura varieties are of abelian type, which means by work of Kissen, they have canonical integral models. And so Kirti Matapusi and I proved the same theorem, but on the canonical integral models, using the exact same method. The hard part is actually defining the cycles in the first place. And next week, I'm supposed to give a talk in the research conference And I'll talk about some version of the Kudla-Millson theorem, but on a toroidal compactification of the orthogonal Shimura variety. But that's not for today. Okay, let's save that. Okay, the proof that Kudla and Millson give and the proof of Brunier, Ram, Zhang, and Borchards have virtually no overlap. They're totally different. And I want to explain the Kudla-Millson proof because, one, I've been thinking about it a lot lately, and two, there's something really special about this situation, about this proof that doesn't appear here, which is, and if you take away one thing from this talk, it should be the following. Kudla and Millson, obviously I've set things up so that these generating series are supposed to be analogous to theta series. Kudla and Millson proved that this is modular by proving that this generating series is a theta series in a very literal sense. It's modular because it's a theta series, and all theta series are modular. But it's not a theta series in the sense of Jacobi and Siegel. It's a theta series in the sense of Weil. And so I have to explain to you how Weil thinks about theta series. My notes say this is section 4, but I don't remember what the, who knows. So theta series. After Weil. Okay, so let's keep our quadratic space, but let me allow it to have arbitrary signature for a moment. So now V has any signature. But I want to assume that its dimension is even. Because I want to avoid half-integral weights and things like metaplectic covers. Let's just stay away from that. And again, we're going to fix a lattice. So how does Weil think about theta series? So for any d, which is always sort of our codimension, there is something called the Weil representation. So I'm going to call it omega of the real points of the symplectic group on the space of Schwartz functions. Schwartz functions on d copies of V tensor R. I mean, in my notes, I wrote down equations that define the Weil representation, but I'm not going to write them on the board. I'm just going to say the following. So the Weil representation is really strange. It somehow started life in physics, where people somehow noticed that certain differential operators that appeared in quantum mechanics satisfied the same commutator relations as elements in the symplectic Lie algebra. And so just formally, that gives you a representation of the symplectic Lie algebra on this Schwartz space by certain differential operators. And then people started asking the obvious question, well, if you have this representation of the symplectic Lie algebra, does it come from a representation of the group? And the answer is yes, that's the Weil representation, at least when the dimension is even, and if the dimension is odd, you have to pass to the metaplectic double cover to define it. But it's not easy to write down what this representation of the group is. You write it down by writing down how generators act. So you start by writing down, there are very explicit pretty formulas for, well, pretty may be an exaggeration, but explicit formulas for how the Siegel parabolic of upper block triangular matrices acts. And then to generate the whole group, you just need to specify the action of one other element, which is the element in the Weil group that conjugates the Siegel parabolic to its opposite parabolic of lower triangular matrices. And that element acts by the Fourier transform on the Schwartz space. And then if you want to know how an arbitrary element acts, good luck. You have to factor it in terms of these generators. which in practice is not something that one really does. In practice, you go back and look at the action of the Lie algebra, which is completely explicit. But I'm not going to write that down either because it's just a bunch of differential operators that aren't terribly enlightening. There's a more enlightening way to write it, but that would require a separate lecture. Okay, so there is such a thing. Great. So Weil wrote down, there were other people who wrote it down essentially at the same time, who proved the existence of this representation of the group. But it was Weil who somehow recognized that this was related to the work of Jacobi and Siegel. So given any Schwartz function define a theta function. So here G is going to be an element of the real symplectic group. So theta L G phi is, you take your Schwartz function phi, you use the element G of the symplectic group to translate your Schwartz function to a new Schwartz function. So that's a new Schwartz function, which I then sum over all. So it's a Schwartz function on d copies of this. So I now sum over my d tuples of lattice points the value of that Schwartz function. That's the definition. And the result, what is the result? Well, it's some smooth function on the symplectic group. And you can check, which in the end amounts to, like I said, the Fourier transform was somehow involved in the definition of the Weil representation. So you do some calculations, at some point you invoke Poisson's summation, and you can show that this function on the symplectic group is left invariant under the action of some arithmetic subgroup that depends on the lattice L, but not on the Schwartz function. Well, what do you do with that? Okay, so now if you look in like Bump's book on automorphic forms, he explains very carefully how to go back and forth between classical modular forms on the upper half plane and automorphic functions on adelic points of GL2. And the first step is to take your function on the upper half plane and convert it into a function on GL2R. And you can kind of do the same thing here. You can go back and forth between functions here and functions on the Siegel half space. And how do you do that? Well, inside of the symplectic group, there's the standard maximal compact subgroup, which is a compact unitary group, U of D, which is, okay, you write your symplectic matrices in block form, and you look at those that look like A, B minus B, A, such that A plus I, B is in the unitary group. So I claim that matrices of this form where A and B have this property is actually a maximal compact subgroup of the symplectic group, and I'm identifying that with the unitary group in this way. What is this? So there's another way to characterize this maximal compact subgroup, which is the symplectic group acts on the Siegel half space, and this is the stabilizer. The stabilizer of everybody's favorite point in the Siegel half space, tau 0, which is just I times the identity in the Siegel half space, which remember lives inside of d by d complex matrices. So that matrix lives in, because its imaginary part is visibly positive definite. Okay, and then a little lemma, which is the following. There is a bijection. Between, smooth functions little f on the Siegel half space. So Siegel modular forms of a given weight, except I don't want to demand that they be holomorphic, just smooth functions that transform like a Siegel modular form of weight m under that gamma L and smooth functions capital F on gamma L mod SP 2D R. Such that under right multiplication by this compact unitary group inside of the symplectic group, they transform in the following way. So capital F is a complex valued smooth function on this quotient such that when you right multiply by an element of the unitary group, it multiplies by the determinant taken in the unitary group to the nth power, f of g, for all u in our unitary group. And okay, I mean, I don't know how helpful it is, but I'll even tell you what the bijection is. So I had to look it up. But it's the first step in going back and forth between classical Siegel modular forms and automorphic representations of the symplectic group. So given by, you take one of these smooth functions on the Siegel half space and you send it to the function on the group, f of g equals c times I plus d. There's almost certainly a determinant of ci plus d to the minus m power f of g acting on our base point tau 0, where I'm writing my element of the symplectic group as a, b, c, d. So that's the bijection. If you start with a little f that transforms like a Siegel modular form of this weight, then the capital F that comes out will be an eigenvector for the action of the compact unitary group inside of the symplectic group. And so the point of this, the upshot, is what does Weil think a theta series is? Weil really thinks a theta series is just a choice of Schwartz function that transforms in a particular way when the Weil representation acts, when you restrict it to the maximal compact subgroup. Because then if your Schwartz function is an eigenvector for the action of u of d, then this theta function will be an eigenvector for the action of u of d, and you can apply this lemma to convert it into a Siegel modular form, possibly non-holomorphic. But that's okay, we like those too. So the upshot is that any phi that is an eigenvector the action of u of d gives rise to a theta function on the Siegel half space. So for example, okay, so where is the theta function of Siegel that I wrote down at the very beginning? I just have to give you a nice choice of Schwartz function. So here it is. So now assume that V is positive definite. And take, so if x, take for x equals x1 to xd, the d tuple phi of x equals you just take the standard Gaussian. So the product from j equals 1 to d of e to the minus 2 pi quadratic form on ej. That defines the Schwartz function on d copies of VR. And you apply it. You can check now if I had written down the explicit formulas for the Weil representation, or at least the infinitesimal form of it. It's a pleasant exercise to check that this is actually an eigenvector under the action of the maximal compact subgroup. You apply all of this machinery, and you get back the Siegel theta function. This recovers Siegel's theta L of tau. Make sense? Sound good? Really sweating up here. I'm running out of water. So I have 20 minutes now? Yep. Okay. Okay. Section 5-ish. Kudla-Millson forms. Okay, back to our Shimura variety. Okay, so after Weil, a theta function is really just a Schwartz function with nice properties. By the way, this is, I mean, okay, there are, what you don't learn in Sayre's book or any first course on modular forms, there are variants of the Jacobi theta series where you have this quadratic space that's positive definite, and if you fix a homogeneous harmonic polynomial of some degree on your quadratic space, you can form the same theta series, but you weight the vectors by evaluating the polynomial. You get these weighted theta series. It just corresponds to, if you take this standard Gaussian and multiply it by a harmonic homogeneous polynomial, it's still an eigenvector for the unitary group. I mean, it's just checking that when you differentiate the action of the Weil representation, being an eigenvector says that your Schwartz function satisfies some differential equations. And when you put in a polynomial here and ask, does my polynomial still satisfy the right differential equations to be an eigenvector, it just says that your polynomial is homogeneous and harmonic. So, okay. That's, oh no. Okay, so the proof that this theta km q to the t, valued in cohomology. So we're going to go back to just one connected component of our Shimura variety. Is modular, is in 3 easy steps. Just kidding, they're not easy. One is the one that requires a real leap of faith or insight. Construct the Kudla-Millson Schwartz function, which is a Schwartz function, not scalar valued, but valued in closed differential forms on the Hermitian symmetric domain. So this is going to be phi km, which lives in the Schwartz functions on d copies of our quadratic space, but tensored with, so A2D just means degree 2D differential forms on D, and it'll turn out to take values in closed forms. So step 1 is just construct it. Construct something. Step 2 is, well, if you want to apply all of this to it, you have to look at how the Weil representation acts on this, when it acts on the first factor in the tensor product, and show that phi km, show that omega, the Weil representation of u, so for all u in our compact unitary group, this should be the determinant of u to the, what's the sign? Plus, minus, I forget. Right. 1/2 the dimension of v times phi km. Whatever this phi km is, the next step is to show that it's an eigenvector under the action of the unitary group. And then, once you do that, then Weil's machinery kicks in. So then Weil, 3. So Weil then gives us, well, a Siegel modular form, but smooth, possibly non-holomorphic, and valued in closed differential forms. Possibly non-holomorphic Siegel modular form. That I'm still calling the theta km, which, I mean, a priori, is a Siegel modular form valued in closed differential forms. But, I mean, I still have some fixed lattice, and gamma stabilizes my lattice, and it'll turn out that this thing will actually land in the space of gamma invariant closed forms. So A, 2D, gamma mod D, closed. And so if you have this Siegel modular form valued in closed differential forms, then you just take your closed differential forms, map them to cohomology, you get a Siegel modular form valued in cohomology. And then the last step is to take its Q expansion and check that it agrees with the images under the cycle class map of these special cycles. So compute its Q expansion. And show it agrees with with this. That's the strategy. And note, it proves, I mean, this proof tells you something stronger because it's giving you a modularity theorem, not just in cohomology, but actually on the level of closed differential forms before you pass to cohomology. And it's a curious thing that I wrote possibly non-holomorphic. In fact, this is a non-holomorphic Siegel modular form. It only becomes holomorphic after you pass to cohomology. And so, okay, I mean, I have 10 minutes, which I think is just enough time to do step one. I'm going to tell you what the Schwartz function is. And there's different ways of thinking about the construction. The construction in Kudla and Millson uses some extremely elaborate representation theory and makes use of these mysterious how differential operators. And there's some strange thing. I asked Kudla once, what are these how operators? And what he said was that, well, you know, Roger Howe came to me and he said, look, in the universal enveloping algebra of the orthosymplectic super Lie algebra, I found these interesting things. Maybe they're good for something. But that was it. That was the answer I got. But then Luis Garcia found another interpretation of the Kudla-Millson forms. He showed that it was actually a special case of constructions of Quillen that somehow produce, it's a general method of producing interesting differential forms that represent certain cycle classes. And this other interpretation is very useful for computing the Q expansion and showing that these closed forms agree with these cycle class images. But the Quillen interpretation is absolutely useless for proving 2, which you seem to need the Kudla-Millson interpretation to do. I'm not going to explain either the Kudla-Millson construction or the construction that Luis gave using Quillen theory. I'm just going to write down a formula. It's no more or less mysterious than the other constructions, so why not? Okay, so construction. Of phi km. Section something or other. I don't know. 6. Okay, so here's what we're going to do. On our Hermitian symmetric domain, look at the constant vector bundle determined by our quadratic space. I erased the tautological bundle on here, but the tautological line bundle on here is naturally sitting inside of this as a sub-line bundle. Oh, first, it has a bilinear pairing inherited from the quadratic space. And it has a filtration. Because if I fix a point of the Hermitian symmetric domain and look at the fiber of the tautological bundle at that point, that fiber is literally sitting inside of the complex points of V, which means that fiber is literally sitting inside of that constant bundle. So my tautological bundle comes with an inclusion into here, and it's an inclusion as a line that's isotropic with respect to that pairing because it's just part of the definition of what lines I'm looking at. So I get a filtration, which is my tautological bundle inside of its own orthogonal under the bilinear pairing inside of my constant bundle. Okay. And now, you can do the following. if I give you a vector, oh, do I want to say, yeah, in particular, this pairing and this filtration, my pairing now defines some canonical pairing between the tautological bundle and the constant bundle modulo its orthogonal. So the dual of the tautological bundle is canonically a quotient of this constant bundle now. So we get a map. What kind of map do we get? Well, if I take a vector x in the real points of my quadratic space, that vector x determines a constant section of my constant vector bundle. Which then maps to the quotient. Which I identify with the dual of the tautological bundle. So this x gives me a section that I'm going to call S sub x. And if you unpack the definitions, the vanishing locus of this section is that divisor d of x of lines perpendicular to x. So easy fact, d of x inside of d is the locus where Sx vanishes. It's almost a tautology.
So sorry, Ben.
Yeah.
So in the pairing there, so you're saying that the quotient is rank 1 and the pairing is perfect.
Yes. Yeah. It's a perfect duality. Yeah. Between two line bundles. Okay. And now I'm glad that back when I was listing all of the assets at our disposal, I included the fact that our line bundle L had this distinguished metric on it, which then induces a dual metric on the dual line bundle. So the metric on L induces a dual metric on L check. And so I can take the norm of this special section associated to x, and this is a smooth function. On D, vanishing. Precisely on D of x. Okay, so now a little bit of complex geometry. Okay, any line bundle has a Chern class in second cohomology. And if you look in like Griffiths and Harris, because we've all read Griffiths and Harris from cover to cover, if you want a differential form that represents the Chern class, what do? Well, you slap a metric on your line bundle and you take the Chern form of the metric. Okay, we've already got a metric, so what's its Chern form? That omega L in A2 of D be the Chern form of L with our distinguished metric. So the definition is omega L is equal to 1 over 2 pi I d d bar log norm of t squared for any local section T of L. So here I'm doing the usual thing where the exterior derivative is decomposed into somehow the holomorphic and anti-holomorphic parts. And you can check that this is independent of the choice of local section, and so they glue together to give a global differential form that's independent of any choice. Except it depends on the metric, but not on the section. And here's the definition. Okay, it's going to look unmotivated, but I can say a few words about it. So definition. If I take one vector, I'm going to define phi of x to be minus e to the minus 2 pi norm of sx squared times the Chern form plus I, because why not, d bar norm of sx squared wedge d norm of sx squared divided by the norm of sx squared. So what is this thing? It's a 2 form in the Hermitian symmetric domain. And it's easy to check that it's closed. I'll let you admire that. So this is not quite phi km. Because this, as a function of x, it does not actually decay rapidly. It looks like it does. Like imagine scaling x, and you think, well, this exponential factor is going to go to 0, right? But it doesn't, because if you happen to be at a point of d where the section sx vanishes, then this exponential factor is 1 no matter how you rescale x. So this is not a Schwartz function of the variable x, but you can fix that by throwing in another exponential. I mean, why not? They're lying around everywhere. So now phi km, so this is just in the d equals 1 case. Is phi km of x is e to the minus 2 pi q of x times this thing that I just wrote down. And the two exponentials together will guarantee that it has rapid decay. And so that's the definition when d is 1. That's the Kudla-Millson Schwartz form. And then for general d, you just wedge them together for a d tuple. x1 up to xd, phi km of x is defined to be phi km of x1 wedge phi km of xd. And that's step 1. I have constructed it. Step 2, I mean, okay, you should believe that if one writes down explicit formulas for the infinitesimal version of the Weil representation, and you've got this explicit formula, you can just, the Weil representation will act through differential operators. This phi km being an eigenvector for the compact unitary group amounts to checking that it satisfies certain differential equations in the variable x, which you can do. It's not very pleasant, but it works. And then, like I said, you're left with the problem of showing that these differential forms that you've constructed actually, when you pass to cohomology, are representatives for the appropriate cycle classes. And I mean, I don't have any time left to say anything about that. I'm already like 2 minutes over time, but let me just say something about this, because if you stare at it long enough, it doesn't look quite so crazy anymore. You should imagine what happens. So my Sx is a section of this vector bundle, L check. So that means if I take the Chern class of L check in cohomology and the cycle class of the divisor of Sx, which is dx, they're going to give me the same class in cohomology. That's almost the definition of the Chern class of a line bundle. And so you have these two different ways of thinking about this same cohomology class in terms of the section or in terms of the line bundle itself. Imagine I take x and just start rescaling it. Okay? What happens to this expression? If I scale x all the way down to 0, this is 1, and you can check that this goes to 0. So if you scale it all the way down to 0, you just get the Chern form of L, but there's a minus sign out front, so you actually get the Chern form of L check. So you should think of this as like a deformation of the Chern form of L check. What is it deforming to? Well, rescale x, but let the scaling parameter go all the way off to infinity. Well, okay, then that's more interesting. It's not entirely clear what happens. But what happens is that this form converges to the Dirac delta current associated to the vanishing locus of the section. Meaning, if you take like a compactly supported test form, integrate it against this with a parameter in front of the x, you compute that integral, and then let the parameter go to infinity. That will converge to the integral of your test form along the divisor d of x. So this is somehow a deformation from the Chern form toward this particular divisor. So it's not an insane thing to look at, but I'll stop there because you want me to. Thank you.
For long questions or further questions on step 2 and 3 this afternoon. If you have any short question, we have maybe time for 1 or 2. Anybody? Yes.
So maybe I missed you. I think you said it's maybe in like some other contexts where we have something else than the symplectic group probably, and we don't have a Shimura datum. We can still somehow
this construction won't work.
Okay, so
is Romain Branchereau here? I've never met him, but if he's here, that's the okay, ask him. He's the person to ask. This won't work, but there's something else that will. You leave Quillen theory and you use Mathai-Quillen theory, which he can tell you about.
Thanks.
Any other quick question? If not, let us thank Ben again.